So far we've done simplifying, we've done evaluating, okay? What does solve mean? Okay, I know it is a scary question. So can you turn to your partner? Claire, you can turn around. Um, Mustafa, you can turn around, talk to Timur. What does it mean to solve? Elian, turn around. Solve quadratic, solve any equation. Yeah. How's that? Find value of x, y, z. Find the value of variable. Luke, that is all solve means. So if you see the word solve, you're going to be getting an equation because you can't find the value without an equal sign. So it needs to be, so you can only solve equations and you can simplify expressions, right? So let's write that down because that's some math terminology. Simplify, absolutely. Expressions, solve equations. Okay, that's what we do. That's the meaning of life, I'd say. Now, when we were solving equations in grade 9, like x plus 3 equals 5, how many different answers were there? Show me with your finger. X plus 3 equals 5. How many possible answers are there? Uno, just one. What is the exponent of x in x plus 3 equals 5? 1, right? If I have like x plus 3 equals 5, what's the exponent of x? It's just x, right? The answer is 2, but the exponent is 1. And that means there is only one answer or one solution. Well, when we have a quadratic equation, what is the exponent of x? And just take a wild guess. How many solutions or answers will there be? Most of the time, there will be 2. Okay. So let's look at what we're going to do today. We're going to understand the concepts. Okay, more words, roots, zeros, x-intercepts, solutions. They are all very similar, but there's a slight nuance. Okay, so what are they? Those are the words we're going to put on our terminology list. Next, you're going to know the 3 cases. Shh, please. 2 real roots, 1 real root, no real roots. Then we are going to define imaginary numbers. What? Then we are going to determine complex roots, more words, or imaginary roots. Okay, do you see how many terms we're learning here? And lastly, we will solve quadratic equations by completing the squares and factoring. We've done that before, but now we're going to do it with complex numbers. The solutions or roots to a quadratic equation in the form are the x-intercepts or zeros of the corresponding quadratic function. Whoa, let's break that up. Okay, when I have an equation like this is a function, meaning you could draw it, you can graph it. Okay? Can you graph this? Tell me why you cannot graph it. And why you can graph the green one. Give it a shot, Ben. No, there are 2. Why can't you graph the purple, but you can graph the green? What does the green have that the purple doesn't? Timur.
The green have y equals and
Yeah, so the green one has a y, meaning you can find points. there's a y-axis and an x-axis. In this purple equation, this is not a function because we don't have a y. A function is also a relation between two variables. Well, how many variables are there in this purple equation? There's one variable. Okay, so this is not a function. Please stop talking. Do we see the difference? Okay, so this is a variable, so this is a function. So this one is not a function, where the green one is a function. Because there is a relationship between the x and the y. So I can graph it, right? Let's say can be graphed. And this one cannot be graphed. So if you have a quadratic equation, you're still going to have your two solutions, right? It's just that you can't put it on there. It's not a parabola. You have a parabola when you have that y equals. Okay. So when you have a quadratic, okay, so this is a quadratic equation. And in a quadratic equation, you're going to have solutions or roots. So the answer, like x equals 5, that is a solution, or we could also say that is a root. When we have a quadratic function, and it can be graphed, we can say, yeah, there's solutions and roots, but there's more words we can use. When you can graph it, now, what would you call this dot on the graph? Yeah, it is the x-intercept. So in addition to having solutions and roots, we also can say that a quadratic function now has x-intercepts. And these x-intercepts have a fancy name. The fancy name is it's a zero. Okay. So now we're going to be talking about something called the zeros. And that is just when the parabola crosses the x-axis. What is equal to 0 at the x-intercept? Is it the y or the x? The y, right? The y is equal to 0 at that point. Okay, so this is called a 0. And at that place, y equals 0. So the quadratic function can have all of these words: solution, root, x-intercept, 0. The quadratic equation, the one that doesn't have the y, this quadratic equation, what can it not have? Luke, it doesn't have an x-intercept because it's not on a graph. There's no intercept. And so since there's no intercepts, there are no zeros for that equation. Okay, so it's just a bit of a nuance. Now, as we recall from grade 10, there are 3 scenarios when we draw a parabola. We can have a parabola crossing the x-axis twice. And in this case, we used to say that there are 2 real roots, but let's be more specific. Because the parabola is because we have 2 x-intercepts, here we say these are 2 real zeros. And we also use the term distinct. 2 real and distinct. What does distinct mean? Their own, like they're not the same. Zeros. Okay, so in this scenario, we have 2 zeros and they aren't the same. In the second scenario, where the vertex is on the x-axis, now keep in mind, this quadratic function could have been like upside down, right? As long as the vertex is on the x-axis. In this case, we use two phrases. Sometimes we'll say 1, 0 because it only touches the parabola, the x-axis once. However, there are still two solutions because it's x squared. So in fact, we say two real and identical zeros. So again, 0 just means x intersect. And in the last case, how many zeros are there? Yeah, Greg is like, none. Well, that's really nice in grade 10, but in grade 11 there are zeros. Okay, so we do say no real zeros, but we do have two zeros. We call them complex, okay, or imaginary, because we're going to use imaginary numbers in this case. So we say two complex or imaginary and distinct. So they're always going to be different. So when I ask how many solutions are there in that case, now we don't say, oh, there aren't any. No, now there are solutions. Okay, there are two distinct solutions and they're going to be complex. So when the parabola does not cross the x-axis, that's a case of having imaginary zeros. All right. So how is it that we find these solutions? How do we solve? Well, one of the ways that we solved in grade 10 is we solved by factoring. Okay. So, and we talked about using the zero product property. Okay. What is the zero product property? So this is when you take a quadratic equation and you factor it, and then each binomial can then be set to equal to 0. So if we want to take this quadratic, is it a function or equation? This one. It's a function because it has a y. Okay, so the first thing we do is we're gonna make it into an equation. So to solve it, we have to set y equals to 0. And so now we can rewrite this function as 0 equals 3x squared minus 8x plus 4. We did this back in grade 10. Maybe we just didn't, yeah. All right, and now we factor. So I'm looking for two numbers that add up to negative 8, multiply to 3 times 4 is 12. So 12. Anyone got them? Yep. Nice. Okay, so we got negative 6, negative 2. So now I rewrite. And you'll see by the end why it is that we had to set it to 0. Okay, and now we factor by grouping. So common factor is 3x. We get x minus 2. And then the next, what's the common factor for the next one? Yeah, minus 2, x minus 2. Beautiful. And so we've got x minus 2 and 3x minus 2. And I need to keep that 0 there. And so once I've got it factored, this is when I bring in the zero product property. The zero product property, please don't talk. Can I have you move your desk 2 feet to that side? I'm just going to make my life easier. 2 feet. 2 feet. That's better. All right. The zero product property means anything times 0 is 0, right? Miss Slide times 0 is 0. So in order for this to be true, one of these binomials needs to be equal to 0. That's how we find our solutions. So we take the first one, we say, okay, in this case, x minus 2 equals 0. What does x have to equal in order for that to be true? Yeah, so x equals 2. Or the second case would be where 3x minus 2 equals 0. Right, go ahead and solve that. I hope some people are able to do this part in their head already. So we got 2 over 3. So these are the two possibilities. These are the two possible solutions that would make this equation equal to 0. And that's how we find our solutions. And so now we have to state that. So how do we write a statement with our solutions? We'll say, therefore, the zeros are, and now why did I use the word zeros? Well, because if I look at the original question, I was given a function. Oh, and they actually asked, they said what determined the zeros or the x-intercepts, right? So I'm not going to say the solutions or the roots. I'm going to say, hey, we're talking about a function, so there are zeros. And what do zeros look like on a graph? Well, they're a point. So that means I can give coordinates, right? I can actually give coordinates of 2 points. So for one of them, x is 2. What's the y? Yeah, the y is 0. And then 2 over 3 and 0. So it would not be a full solution to say, therefore, x equals 2 or x equals 2 over 3. That is not a complete answer. Okay, because you're not showing me that you understand we started with a function, then we took that function and wrote it as an equation so that we can find those x-intercepts. Did I answer your question?
Yeah, instead of saying the zeros, you say the x-intercepts.
Yes, you could have said zeros or you could have said x-intercepts. All right, let's try again. Okay, thank you. In this case, in example 2, are you given an equation or a function? Equation. There is no y. So this is an equation. So when we solve, what are the two words that we find? Are we finding a 0? No, it's not. So we can find what? Okay, we can find a root or solutions. Okay? All right. So first things first, let's clear out those fractions. So I need to multiply every fraction by the same number, and it has to be a number that will clear every fraction. What's the number? Yeah, so will 6 clear a denominator of 6? Yes. Will it clear 3? Yes. And then a common mistake is that someone will say, oh, I don't need to multiply it by the 2 because it's not a fraction. But we have to multiply every term in the equation by the 6.
I'm sorry, Miss Love.
Yes?
Why do I need to multiply first time if it's already have 6?
Why do you need to multiply which one?
First time, like x to the power.
Because we're trying to get rid of the of the denominator. So this is divided by 6. This is times 6, so they cancel each other out. Thank you. 6 and 3 cancel, and that becomes a 2. So I get 2 times 4 is minus 8x. negative 2 times 6 is minus 12. In order to factor this, in order to use the zero product property, I need to have a 0 on one side of the equal sign. So let's bring the 12 over, right? We could say, okay, plus 12, plus 12. Or if you just know to bring the x over to the 12 over to the other side, it becomes positive. And now to solve, we're looking for two values that make this equation equal to 0. Oh, so we need to factor. Some people are still using decomposition for a simple trinomial. Please don't. It's way too much work. You're working way too hard. So I'm looking for two numbers that add up to negative 8 multiplied to positive 12. What are they? Yep. So when you're doing decomposition on this question, you're actually doing the work twice. Okay, and the solution is, how do we make all of this equal to 0? Well, the first bracket, Liam, I'm going to ask that you sit in that desk. I love that you're having a good time. Pardon? Are you really?
Yeah, she is.
Oh my God. And I don't want to stop that because I get that's how you learn. Does it distract people? I mean, it maybe just distracts me. Okay. All right. So what does x have to equal for this first binomial to be equal to 0? X equals 6 or x equals what? 2. All right. So go back to the question. Are we looking for solutions and roots, or are we looking for x-intercepts and zeros? Roots, good, because it's not a function. And so then we can say, therefore, the roots are. Now, is this on a graph? Do we have coordinates of a point? We do not. So in this case, all we say is the roots are x equals 2 and x equals 6. Okay, so that's a nice review of what we did last year with a little bit of new vocabulary. Let's bring in some complex numbers. Yeah.
What's the difference between a root and a solution?
Nothing.
So it's just the same
So
thing.
those two are okay. Solution is broader. A linear equation like x plus 2 equals 5 can have a solution, but it can't have a root. Okay? So a root is specific for a quadratic and maybe higher. All right, let's imagine. Okay, here's the question. We've always talked about the fact that you cannot take the square root of a negative number, right? The answer to negative 4 is nothing, cannot be done. Well, it's half right. Okay, there are no real root. There's no real value for this, but we can bring in something called an imaginary number. And an imaginary number, okay, this is quite tricky. We use the letter I to represent the square root of negative 1. Not negative 1, okay? I does not equal to negative 1. I equals to the square root of negative 1. So that also means that I squared is negative 1, right? Because if I have, okay, watch this. If I have I times I, well, what is I? I is negative 1. So what's negative 1, root negative 1 times root negative 1? Remember when we square a square root, you just get rid of that square root? So that means that I times I is negative 1. Okay? So I squared is -1, and the square root of I is -1. Don't worry if you don't understand it. These are just two that we will use to help us out. And so we call I an imaginary number. Okay, so let's see how we can do this. Now, when we have imaginary numbers, okay, um, we're going to have we're starting to work in a number system called the complex numbers. So in grade 9, we learned about real numbers and complex numbers. And it was like, hey, at some point, folks, you're going to learn about complex numbers. And that moment is now. It's like complete circle. All right, so let me show you how to do this. So square root of -5, we no longer say cannot be simplified. What we say now is, hey, square root of -5 is also the square root of 5 times -1. Okay, so just follow along and ask me questions at every step. Yeah, 10, 15. Which also means that we can break it down into two roots, right? Root 5 times root -1. Okay, well, we just learned that root -1 can be written as what? As I. And so this is how we can actually rewrite root -5 as an expression of complex numbers. Okay, let's look at the next one. So root -49. Okay, that's the same thing as saying 49 times -1. And so we can break it up into root 49 times root -1. Oh, and look, root 49 would be what? Good. And root -1 would be I. Okay. So that I is just a way to take that -1 out of the square root. Lastly, here we have a real number added to a complex number, to an imaginary number. So we don't change the 3, but we break up the -3 into root 3 times root -1. And the only thing I can simplify in this case is that root -1 is just written as I. And notice the I always goes at the end. And I cannot combine, I can't add a real number and a complex number, right? These cannot be added. All right, let's look at example 4. So now we're going to solve a quadratic function that will have complex roots. Okay, find the roots or zeros of this quadratic function. All right, step 1 is we're going to set y equal to 0 so that we're working with an equation. And so when we are solving, this is a bit different because we're not going to be factoring because it's not in standard form. But we still want to find out what the x is. So, oh yeah, to find x, can we not isolate x? Can we not move everything to the other side of the equal sign? So which part of this equation is easiest to move first? Yeah. So I'm going to add 8 to each side, right? So I get 8 equals negative 2 x minus 2 all squared. I want to get at the x, right? So I'm sort of chipping away, moving, dividing, multiplying, using opposite operations to get at the x. All right, what is the next opposite operation I can use? Sebastian? Beautiful. I'm going to divide everything by negative 2. That means these cancel out. Okay, it's starting to look good. 8 divided by negative 2 is negative 4 equals x minus 2 all squared. Okay, what's the next opposite operation, Mustafa? Yes. So it's the bracket is squared. So the opposite of that is to square root it. And we square root this negative 4. Now, watch this. Because there is an x involved. Okay, everyone look here. Because there is an x involved, when we take a square root of a number, we also add a plus or minus in front of the square root. Okay, we'll see what that means shortly. So I've got plus or minus root negative 4 equals x minus 2. I'm almost there. What do I do now? Sure. Add 2 to both sides. Now watch how I write it. We first write the real number, then we write the complex number. Now instead of writing negative 4, how can I simplify that? Okay, let's break it down. You're going to give me the full answer, but I want to first break it down. So I know I can write negative 4 as root 4 root negative 1. Okay, root 4, that's just 2. Root negative 1, that's I, right? So I'm saying 2 plus or minus 2I equals x. Do you see why that plus or minus is helpful? Why? That's right. We need 2 zeros. Are we looking at 0? Yeah, we need 2 zeros. Right? So what that means is, therefore, the zeros are, and now we're going to write them as a point, right? We're going to say, okay, the first one is 2 plus 2I, comma 0. And the second one is 2 minus 2I, comma 0. What type of roots are these? Sorry, what type of zeros are these? 2, oh wait, I want a different color. Okay, are they real or distinct? Oh, sorry, are they real or imaginary? Are they identical or distinct? Okay, 2 imaginary and distinct roots. So that means if we were to draw the parabola, it's not that the parabola doesn't exist. It's just that we don't see it crossing the x-axis. So the big trick today is, the big reminder is when we're taking the square root of an expression that has an x, we take the number part gets a plus and minus sign in front. Okay? You'll say, why didn't we do that before? Well, because earlier we weren't working with a variable. Okay? And it's time, Marley?
Yeah,
I
10:14.
yeah.
I'm going a minute ahead.
Oh, you're excellent. I know, right? And it was kind of like we got there. So yeah, I think we're good. All right, let's do the tests and quizzes. Thank you. Oh yeah, folks, can you move the desks as I do this? Yes, you may. Folks, as soon as I get your quiz, if you gave me your quiz, you can expect a mark update shortly. If you didn't give me your quiz yet, you can send me a picture so I can give you a mark update faster. Oh, let me stop recording.
So I actually don't know what you might